also design drainage steps involved in road construction. Welcome to Blueprint to Reality. Welcome back to Blueprint to Reality, your go-to channel for unraveling the marvels of civil and structural engineering. If you're fascinated by how roads are built and how infrastructure comes to life, you're in the right place. Don't forget to like, share, and subscribe so you don't miss any of our engineering deep dives. Introduction to road construction. Road construction is much more than laying asphalt on the ground. It's a meticulous process involving planning, designing, and executing each step with precision to create safe and durable roads. Roads are the lifelines of modern civilization, connecting cities, supporting economic growth, and enabling daily commutes. Today, we'll walk you through the key steps involved in road construction, highlighting the science and engineering that makes our journeys smoother and safer. 1. Planning and surveying. The first step in road construction is planning and surveying the site. Engineers study the geography, soil types, and traffic patterns of the area to determine the best route and design for the road. Advanced tools like GIS, Geographic Information Systems, and GPS are often used to map the terrain accurately. Surveys also identify potential obstacles like rivers, hills, or existing infrastructure that may influence the route alignment. This stage is crucial for ensuring the road's feasibility and long-term functionality. 2. Design and alignment. Once the planning phase is complete, engineers move on to designing the road. This includes deciding the road's alignment, width, gradient, and cross-section. Proper alignment minimizes sharp curves and steep slopes, enhancing safety and driving comfort. Engineers also design drainage systems to prevent waterlogging and extend the road's lifespan. Computer-aided design (CAD) software is often used to create detailed blueprints and simulations of the proposed road layout. 3. Clearing and excavation. Before construction begins, the site is any vegetation, rocks, and other obstructions. Excavation work follows, where earth-moving equipment like bulldozers and excavators are used to remove excess soil and shape the terrain according to the design. If the soil at the site is unsuitable for supporting the road, it may be replaced or treated to improve its strength and stability. This step prepares a solid foundation for the subsequent layers of the road. 4. Subgrade preparation. The subgrade forms the base of the road and plays a critical role in its overall stability. The soil is compact with the desired density and strength, ensuring it can bear the weight of the traffic and road structure. Sometimes, tiles or other reinforcement materials are used to enhance the subgrade's performance. Proper subgrade preparation is essential for preventing road failures like potholes or cracks. 5. Base layer construction. Above the subgrade, a base layer of crushed stone or gravel is laid to distribute the loads from the road's surface. This layer provides structural support and helps with drainage by preventing water from seeping into the subgrade. The base layer is compacted using rollers to achieve a uniform and stable surface. In multi-layered road construction, an additional sub-base layer may be added beneath the base layer for strength. 6. Paving the surface. The layer, which we commonly refer to as the road, is laid on top of the base. This layer can be made of asphalt, concrete, or other materials, depending on the roads and budget. Asphalt is high temperature and spread evenly over the base layer using paving machines. Once laid, the surface is compacted to achieve a smooth and durable finish. For concrete roads, the material is poured, leveled, and allowed to cure for several days. 7. Markings and finishing touches. After paving, the road is marked with lines and symbols to guide traffic. This includes lane dividers, pedestrian crossings, and directional arrows. Reflective paints or thermoplastic materials are used to ensure visibility at night. Additional features like guardrails, signboards, and lighting are installed to enhance safety and usability. Landscaping along the roadside may also be done to improve and control erosion. 8. Quality control and maintenance. The final step involves thorough quality checks to ensure the road meets safety and durability standards. Engineers test the pavement's thickness, compaction, and smoothness to detect any deficiency. Regular maintenance, such as patching potholes, resealing cracks, and cleaning drainage systems, is also planned to extend the road's lifespan and keep it in optimal condition. Conclusion: building roads for the future. Road construction is a complex and collaborative effort that combines engineering expertise, advanced technology, and meticulous planning. From surveying and designing to paving and maintenance, each step is essential to creating roads that are safe, durable, and efficient. As we continue to innovate in materials and techniques, the roads of the future will be even more sustainable and resilient. Thank you for joining us on this journey through the steps involved in road construction. If you enjoyed this video, give it a thumbs up and share it with others who love learning about engineering marvels. Subscribe to Blueprint Reality and hit the notification bell so you're always updated on our latest content. Until next time, keep exploring the fascinating world of engineering. The difference between highways and expressways. Welcome to Blueprint to Reality, where we simplify engineering concepts and infrastructure design. Today, we're diving into the difference between highways and expressways, two essential road types that shape transportation networks worldwide. Though often used interchangeably, highways and expressways have distinct features, speed regulations, and access controls. Let's explore what sets them apart. Definition and basic purpose. Both highways serve as major roads for vehicle transportation, but their purpose and design philosophy differ. Highway, a general term for any major road that connects cities, towns, and rural areas. Highways can have intersections, traffic signals, and varying speed limits. They may be two-lane or multi-lane and accommodate mixed traffic, including pedestrians and bicycles in some cases. Expressway, a controlled access road designed for high-speed travel with minimal interruptions. Expressways have limited entry and exit points, no traffic signals, and separate lanes for opposing traffic to ensure smooth vehicle flow. While all expressways are highways, not all highways qualify as expressways due to differences in design standards and access control. Road design and lane configuration. The design of highways and expressways varies based on traffic volume, safety concerns, and intended travel speed. Highways can be single-lane or multi-lane and may include intersections, roundabouts, and pedestrian crossings. Some highways pass through urban areas, meaning lower speed limits and more frequent stops. Expressways are designed for fast, uninterrupted travel with multiple lanes, usually 4 or more, separated by medians or barriers to prevent head-on collisions. The design minimizes sharp curves and inclines to accommodate high-speed movement. Expressways prioritize efficiency and safety, making them ideal for long-distance travel and high-traffic corridors. Access control and entry points. A key distinction between highways and expressways lies in access control, how vehicles enter and exit the roadway. Highways may have multiple access points, including driveways, intersections, and local roads connecting directly to them. This can lead to traffic congestion, especially in urban areas. Expressways feature limited access points with controlled on-ramps and off-ramps. Vehicles cannot directly enter from side roads or properties, reducing traffic conflicts and improving safety. This access control makes expressways faster and safer, but also means drivers must plan exits in advance. Speed limits and traffic flow. Since expressways are designed for high-speed travel, theirs are generally higher than highways. Highways have varying speed limits depending on location and traffic conditions. In urban areas, speeds from 50 to 80 kilometers per hour, 30 to 50 miles per hour, while rural highways allow speeds up to 100 kilometers per hour, 62 miles per hour. Expressways maintain consistently higher speeds, typically 90 to 130 kilometers per hour, 55 to 80 miles per hour, depending on country regulations. The lack of traffic signals and intersections allows for smooth, uninterrupted movement. Expressways reduce travel time significantly compared to highways, making them ideal for long-distance and intercity travel. Intersections and traffic control devices. Another major difference is how traffic is managed at road crossings. Highways often have intersections, roundabouts, or even traffic lights at various points. Some highways feature flyovers or underpasses at busy junctions to improve traffic flow, but many still require vehicles to stop or slow down. Expressways eliminate traditional intersections, relying instead on grade-separated interchanges, such as overpasses, underpasses, and cloverleaf junctions. This ensures continuous traffic flow without stop-and-go delays. This difference enhances safety and efficiency on expressways compared to conventional highways. Whole system and maintenance. Both highways and expressways require significant investment in construction and maintenance, but funding methods can differ. Highways are typically government-funded and toll-free, although some major highways may have toll sections. Maintenance depends on public funds, which can lead to varying road quality. Expressways are often toll roads, meaning users pay fees to maintain infrastructure. Many expressways use electronic toll collection (EDC) systems to minimize delays. Toll expressways generally have better road conditions due to dedicated funding, upkeep, and Safety and accident rates. These expressways have better access control, lane separation, and fewer conflict points. They tend to be safer than highways. Highways experience higher accident rates due to intersections, mixed traffic, and pedestrian crossings. Sudden stops and unpredictable vehicle movements increase collision risks. Expressways have significantly lower accident rates since they eliminate conflicts from oncoming traffic, pedestrians, and cross traffic. Vehicles move at uniform speeds, reducing the likelihood of crashes. However, accidents on expressways can be more severe due to higher speeds. This is why expressways incorporate barriers, rumble strips, and emergency lanes to enhance safety. Common examples and expressways. To better understand the difference, let's get some real-world examples. Highways. OUS Route 66 USA. A historic highway with multiple intersections and access points. Golden Quadrilateral, India. A network of national highways connecting major cities. A6 Highway, UK. A major road connecting urban and rural areas. Expressways. Interstate 95, USA. A high-speed, limited-access expressway along the East Coast. Yamuna Expressway, India. Toll expressway with controlled access and high-speed travel. Autobahn, Germany. A world-famous expressway known for its sections with no speed limit. Conclusion. Highways and expressways are both essential to modern transportation, but they serve different roles. Highways provide connectivity with more frequent access points, while expressways prioritize speed, safety, and efficiency by limiting interruptions. Understanding these differences helps engineers, planners, and travelers make better decisions about road networks and transportation strategies. Thank you for joining us on Blueprint to Reality. If you enjoyed this breakdown, don't forget to like, subscribe, and stay tuned for more insights into civil engineering and infrastructure design. See you in the next video. The role of drainage in road design. Welcome to Blueprint to Reality, where we bring the engineering principles shaping our modern infrastructure to life. If you've ever wondered how roads withstand heavy rains and floods, today's video is for you. Let's dive into the essential role of drainage in road design. Why drainage matters in road design. Water is one of the most destructive forces for roads. Without proper drainage, roads are exposed to surface water accumulation, leading to hydroplaning and increased risks. Structural damage. Water can weaken subgrade, causing cracks and deformation. Erosion and environmental impact. Poor drainage can lead to soil erosion and damage to nearby ecosystems. Drainage systems are designed to manage these risks by effectively channeling water away from the road structure. Components of a road drainage system. 1. Surface drainage. Roll. Removes water from the road surface. Features: cambered roads with a slight slope and gutters ensure water flows to designated channels. 2. Subsurface drainage. Roll prevents water from seeping into the road's foundation. Features: includes drain pipes and permeable layers to divert water away from the subgrade. 3. Side ditches and channels. Roll collects water in the road and directs to natural or artificial outlets. Features: these ditches are designed with adequate slopes to prevent stagnation. For culverts and stormwater drains. Roll allows water to flow beneath the road or to cross over natural barriers. Features: these are essential in areas with streams or heavy rainfall. 5. Catch basins and inlets. Roll collect and funnel water into drainage systems. Features: typically found in urban settings, manage surface runoff. Key design principles for effective drainage. 1. Slope design. Roads are built with a crown or cross slope to guide water off the surface. 2. Material selection. Permeable materials are often used to reduce water infiltration into the subgrade. 3. Capacity planning. Drainage systems are designed to handle peak water flow during storms. 4. Maintenance access. Engineers incorporate access points for cleaning and maintaining the drainage infrastructure.